All right. So, welcome. And again, hope you all had a tremendous weekend. We're Tuesday of week 9. Wow. All right, so kinematics. We'll do a recap of some stuff we talked about last year when we do kinematics. Kinematics is basically physics, but we're using calculus techniques to solve physics problems. And I've gathered before the physics class is on now, which means none of you guys do physics. So we'll have a bit of a chat about what the different concepts mean and so forth. So I've got a table here to summarise some of the important concepts. We're going to make a distinction between the word displacement and distance. And of course, intuitively, we use S to represent displacement. And so S of t is going to be displacement with regards to time. Okay? S is displacement, t is time. And let's say you've got a fella called Peter and he walks 10 metres to the right and then 5 metres to the left. Okay, 10 metres to the right, 5 metres to the left. The total distance he has travelled is 15 metres. Okay, the distance is 15 metres. But his displacement is only 5 metres. The displacement is the distance from the origin to where you finish. Okay, that's what displacement means. It just means distance away from your starting position. Alright, so distance, the total amount travelled. Displacement, how far are you away from where you started? Okay, we are also familiar with velocity and acceleration. Velocity is just rate of change. Alright, so if I have v of t is the derivative of s. Alright, remember, if I have y, dy on dx describes the rate of change of y with regards to x. If I have s of t, then s dash of t describes the rate of change of s with regards to t. The change in displacement, rate of change in displacement is velocity, and similarly, acceleration is the rate in change of velocity, which is s double dash of t. Okay, and that's all summarised in a table above there. Okay, we'll talk about speed and so forth as it pops up. Maybe I'll just mention the second dot point. An object changes direction if its sign changes direction in the velocity sign diagram. Velocity is increasing if acceleration is positive. Okay, let's get into it. We've got here the displacement of a particle with regards to time is given by this equation. It's moving along the x-axis. We've got displacement is in metres and time is in seconds. Part A, draw sign diagrams of the particle's acceleration and velocity functions. So that means I want to find the velocity function and draw a sign diagram of it. I'll do that first. So the velocity function is the derivative of the displacement function. So we're going to differentiate this one here. That'll be 3t squared, take 18t plus 15. And we want to draw a sign diagram of it. And we can go straight to our calculator, but I'm getting you in the habit of performing the mathematics for the sake of doing mathematics, right? For the sake of developing those skills. So if I'm going to factorise this, like 3 is common, and I'd have t squared take 6t plus 5, and I could write that as t take 5 and t take 1. All right, so if I'm finding the roots of it, I would have t is 5 or t is 1. So for the velocity sign diagram then, it has a root at 1 and a root at 5. And it's a quadratic. It has a positive a value, so it's opening upwards, which means it's going to be positive, negative, then positive. Now, with kinematics, we only consider positive values of time, which means when we're drawing the sign diagram, all right, we cut it off at 0. We draw a line there to represent that time is 0, and we're only considering positive values of time. If you have a negative root for values of time, you don't even consider it. We're only talking about positive values. So this is the sign diagram of the velocity function. Next, let's find the acceleration function, which is the derivative of the velocity function. So I've got it represented in a number of different ways here. I'm going to differentiate this form because that's already expressed as t to the power of n. So that's going to give me 6t take away 18. All right, that's the equation of a line, isn't it? We've gone from a cubic to a quadratic to a line. So that's 6 times t, that's what that says. 6t take away 18. And if I want to find the root of it, we'll make it equal to 0. And we'll solve through. It's the equation of a line. It has positive slope, which means it's going from below to above. Now, both of these sign diagrams, all right, so this is V of t, make sure we label them. This is A of t. We can get straight off the graph. All right, you can graph this, graph the derivative, you know, get the sign diagram, graph the second derivative, get the sign diagram. So that is part A complete. We've made mathematical argument there. Part B. Find the particle's position and time when it changes direction. Position and time. So let's have a look at the second dot point. An object changes direction if its sign changes in its velocity sign diagram. Okay, so we're looking back up here and I can see the sign changes here. Positive velocity means we're moving to the right. Negative velocity means we're moving to the left. Okay, so if I have a change from positive to negative, I've changed direction. So let's start recording this down. This is part B. Changes direction at t is 1. And at t is 5. Now, it says find the position and time. We've got the time. We want to know the position. We want to know the displacement. Where is it when it changes direction? So we want to know what is the displacement when time is 1 and what is the displacement when time is 5. And for now, all we would have to do is evaluate that. I'm going to leave that for now until I've got it graphed up and I can just G-solve all those things all at once. All right? Okay, part C, part 1. When is the particle's speed increasing? Okay, so there's a difference between speed and velocity. Velocity has direction. All right, so notice how positive velocity means we're moving to the right. Negative velocity means you're moving to the left. Speed is not about direction. Speed is just about how fast are you going. And so they're saying, when is the magnitude of velocity increasing? When is the size of velocity increasing? And you don't even need to understand what it means. Let's just follow the algorithm. This is going to be the third dot point. Speed of an object is the magnitude of its velocity. If V of t and A of t have the same sign, then the speed is increasing. All right, so we're looking at the sign diagrams here and we're going over what intervals are they both positive or over what intervals are they both negative. So I'm going to look first, A of t is negative till we get to 3 and V of t is negative between 1 and 3. They're both going to be negative between time is 1 and time is 3. Okay, so that's going to be the first point when speed is increasing. V of t and A of t have the same sign. From 1 to 3. Okay, they're both negative from 1 to 3. So what that technically means is we have negative velocity and the acceleration is it's accelerating in the negative direction. It's speeding up in the opposite direction. Okay, so that's the first interval. But then after t is 5, they're both positive. All right, so we have another answer here, which is and t is greater than 5. That's when they're both positive. So we have positive velocity and the speed is increasing in the positive direction. Very good. So that's our answer to C part 1. For C part 2, when is the velocity increasing? All right, I'll just take you to the very bottom dot point. Velocity is increasing if acceleration is positive. Okay, that's all it is. If we have positive acceleration, it means the velocity is increasing in the positive direction. So all we'll say here, when t is larger than 3. All right, positive acceleration when t is larger than 3. Okay, part D. Find S of 6 and draw a motion diagram over the first 6 seconds. Hence, find the total distance travelled in the first 6 seconds of motion. So this is the first thing it wants us to do, is find S of 6. Now, what we're going to need for us to draw a motion diagram is all of the important points. So we will find S of 6 in a moment, but I might just list what the important points are. Firstly, they are its initial position, where it starts. They are where it changes direction, and we know it changes direction when time is 1 and when time is 5. And we know we want to go until time is 6. That's where we finish. All right. So what I'm going to do now, I'm going to get all of them at the same time. This is like the optimal way for us to use our time. I'm going to graph this function, okay? Only positive values of x, all right? Positive values of x on the, and then for y, I would just set a big region for y, you know, from minus 100 to 100. And I'm just going to say, what's the y value when time is 0, when time is 1, when time is 5, and when time is 6. So let's go ahead and get those now. We get all of them at the same time. So x to the 3. So positive values of x, and we're only interested from 0 to 6 for x. We don't need to go beyond that. And for y, I'm going to go from, well, minus 50 to 50 should be plenty. Alright, so I'll trace along it. When time is 0, the y value is 0. When time is 1, the y value is 7. And if you're doing that, you're noticing that those correspond with the maximum and minimum points. Alright, we can make a connection there in a moment. When time is 5, we have minus 25. And when time is 6, I have minus 18. All right, so just G-solving all that off our calculator. So what did I do? Graph this function, set an appropriate V window such that I can see the graph, such that I can get this information. When time is 0, what's the Y value? Time is 1, what's the Y value? All right, so just tracing along it, pressing those numbers there. Okay, so once us that, now we don't forget to fill in this part here. S of 1 is 7 meters, and S of 5 is minus 25 meters. They're the locations where it changes direction. All right, let's draw a sign diagram, draw a motion diagram. So a motion diagram is a horizontal axis that's indicative of the movement of an object or particle. So I'm going to draw an axis here, a horizontal axis, and I'm going, what is the point that's furthest to the left and what is the point that's furthest to the right? Because those are going to be the extremities of my motion diagram. So the point furthest to the left is minus 25. All right, that's the extremity out this end. And the point furthest to the right is positive 7. That's going to be here. And then we have 0 in there somewhere. And we have minus 18 in there as well. Those are the interesting points. But notice I've got my point furthest to the left, point furthest to the right. Okay, and then all we're doing is plotting where it is and when it is. So, when time is 0, it's here. The displacement is 0. That's its beginning position. All right? And initially we have positive velocity, which means we're traveling to the right. And after 1 second, its displacement is 7 meters. So after 1 second, it is here. It's moved like this. Okay? But right there, it changes direction and it starts going to the left. All right? And we can confirm that from our velocity sign diagram. It has negative velocity, which means it's moving to the left. And it's moving to the left until it gets to minus 25 meters. So that's all the way to here. Minus 25 meters. And that occurs when time is 5. And you can write those down on the sign diagram, the motion diagram as well. Okay, and here it changes direction again and it moves to the right until it gets to minus 18 when time is 6. Okay, so this indicates what the particle is doing. All right, initially it's moving to the right and then it starts moving to the left and then it starts moving to the right again. Let's point out how that correlates with our velocity diagram. Moving to the right, positive velocity. Moving to the left, negative velocity, and then moving to the right, One more thing, let's talk about the graph of S of t. Okay, so if you graph S of t, so if you've got the same V window I chose, it's a cubic and it looks a bit like this. Okay, let's talk about what's going on here. This is the displacement of the object against time. So you can see as time increases, the object is getting further and further away from the initial position. This is when the displacement is 0, right? It gets further and further away until this point in time. When time is 1, it changes direction. And so its displacement starts coming back. See how it's coming back to where it was? Coming back to where it was. Here, the displacement is 0. That's where it passes this point here. Passing displacement 0. And then its displacement is getting further and further negative from where it began until it gets to here, okay, where it's the furthest away, and then it starts moving back to the right again. Okay, now we are asked though, we're not quite finished, it says draw a motion diagram, find the total distance travelled. Because its final displacement, where it finishes, the displacement is minus 18 metres, but how far has it travelled in total? Well, we can break it up. You can use the motion diagram to support your answer. The distance between these 2 points is 7 metres. Okay? The distance between these 2 points is 7 metres. All right? From here to here, from 0 to minus 25, that's 25 metres. And from minus 25 to minus 18, that's 7 metres. So the total distance that it's travelled then is just the sum of all of those. 7, 14, 21 plus 25 is 46 metres. Very good. Okay, let's let you guys have a crack at 3E, kinematics. Again, it will start easy, it will get harder. There is another example, but I don't think I'll go through it yet. It's pretty well the same skills, just in a more